students will discuss about Biot-Savart law. This law basically is used to find the magnetic induction at a point near a current carrying conductor, whether near a conductor carrying current with straight conductor nearby place, here or anywhere, you can find the magnetic field. If it is a circular coil and current flows through this, it also produces magnetic field. You can find the magnetic field due to circular coil. Due to circular coil like this, we can find the magnetic field at the center or along the axis at any point on the axis. There are these variations that we learn that we can find using Biot-Savart law. In 12th standard, we will be studying about Ampere's law, that is Ampere's loop law. So Ampere's law is much easier than this Biot-Savart law. So we are today concerned only with the Biot-Savart law. The statement says that when current flows through a conductor, the magnetic field at a place nearby at a distance r depends on the current flowing through the conductor, the amount of current flowing through the conductor. It depends on the length of the conductor. The conductor may be having very large length, but then we have to find the magnetic field due to each small elementary length of the conductor, and finally we add them in terms of vector to get the total magnetic field. So it is found that the magnetic field due to the conductor is proportional to the current flowing through it, the length of the conductor, and the angle the current element makes with the point position vector. So this is a conductor. I want to find the magnetic field here to this position vector from the element you choose, from that center of that element to the point where you want to find the magnetic field. This distance, this is your position vector r vector. So that depends upon the sign of the angle between this ideal vector and this r vector, and it also depends on the distance where you want to find the magnetic induction. If the distance is far off, the magnetic induction will reduce greatly following inverse square law. So it's said that the the magnetic induction depends on the current, the length of the element at dl, sin theta and r square. Combining these four relations, we have that if this is a conductor and I choose an element here dl length, current is flowing like this. I is the current flowing through the conductor from the center of it to this point. I take a point here, say this point is P, where I want to find the magnetic induction. So this magnetic induction will be small because the length I am considering is small. So I want to find the magnetic field at this point only because of this contribution by this element of length So this part of the element only. This length is very small. So therefore, it because of this part of the element, the magnetic field here will be also very small. That we write as dB. The magnetic induction, this where this is the magnetic induction due to this element. But when we are talking about the conductor, what is the magnetic induction due to the conductor? So you have to think of the integration, because Biot-Savart law states that dV is proportional to I dl sine theta upon r square. This is what we have just written. That here, this point to this point, this direction is always towards the position where you want to find the magnetic induction. There is a position vector r, and the current is in this direction. Current is in this direction. So we'll just take a tangent to this. Okay. So this is what is the direction of I dl. This is one vector we say. The I dl together is called the current element. This is called current element. This is we treat this as vector. So this vector and this r vector makes an certain angle. Suppose they make an angle theta. As I choose different any other different element. Suppose this is dl1. I choose here dl2 here. From this point, if I join this is my new r, and this r make different angle with this. So in this case, the ideal will be like this, always tangent, and the angle that it makes with this line is different. So similarly, if I choose an element over here, this will be the angle. So the angle theta actually varies with change in the element. So this is one variable. So and also r is also variable, because if the conductor is like that, then different parts of the conductor will be at a different distance from where you want to find the magnetic induction. I want to find the magnetic induction at P, so the position or the distance of that point from here and the distance of that point from here will be different. So these are all variations. So one thing we are keeping constant is the current, that is constant. The current is constant, that is steady current. So combining these four proportionalities 1, 2, 3 and 4, I have dV is proportional to I dl sine theta divided by r square. So in this expression, we will we'll introduce a constant, because this is a proportionality sign. So we have to write in terms of equation, we have to introduce one constant. So this is the expression in proportionality form. I'll convert this into equation. So this dV is equal to some constant I will introduce, I dl sine theta over r square. This k is a constant. It depends on the unit you choose and the medium where the conductor is placed. Depends on unit, and where the conductor is placed. That k is called as mu naught over 4 pi. Mu naught is called permeability of free space. Mu naught is called permeability of free space or vacuum or air. So when conductor is kept in air, you write this k as mu naught 4 pi. If I write that, so this will become mu naught upon 4 pi I dl sine theta upon r square. This is what is this is how we find the magnetic field. And this mu naught upon 4 pi is found to be 10 raised to minus 7, and you can check out that the unit of this will depend on the unit of this, and unit of this divided over here. Sin theta has no unit. This is length, this is a one length, so it is meter is left. 1 meter is left. So this is magnetic induction. This is Tesla meter per ampere. So Tesla meter per ampere. And we also know that the flux, magnetic flux is magnetic field into area. This unit is Weber. This is Tesla. This is meter square. Area is meter square. So Tesla is Weber per meter square also. So if I put here Tesla is Weber per meter square, so it will be Weber per ampere meter. So you can write this unit or that unit, Weber per ampere meter. This is the expression of formula that is given by Biot-Savart law. Biot-Savart to find the magnetic induction at a point nearby a charge current carrying conductor. So this is what is known as the scalar form of Biot-Savart law, and I was supposed to find the magnetic field at point P due to the whole of the conductor, not because of the small part of the conductor. So to find the whole part, we have to integrate this. So when I want to find that, the total current magnetic field at that point due to the contribution from each of the elements is integration of dV, and that limit also varies depending on the situation. So this is mu naught upon 4 pi ideal. So this is what is the formula. We have to integrate it to get the magnetic field. Now we will write the vector form of Biot-Savart law. In scalar form, we write dV like this. We know that magnetic induction is a vector quantity. So if I want to write in terms of vector, and surprisingly there is sin theta over here. In vector multiplications, there are two possible vector multiplication. One is called dot product, another is called cross product. In dot product you have cos theta, and in cross product you get sin theta, because sin theta is there and this is a vector. So I will write the this side of the equation in terms of vector cross product, such that because the result that comes out to be also is a vector quantity, and we can arrange this right hand side in as in the form of A cross B, that is a cross product of two vectors, say A and B, so A cross B. So this is mu 0 upon 4 pi is a constant quantity, has nothing to do with the cross product. So in cross product we will consider two vectors. One vector is obviously the current element, that is IDL. I'll consider this as one. This was one vector. This is my vector AC, and this will be my vector B R. And the angle between the two vectors is theta. This is the point where I want to find the magnetic induction. So these two vectors, I'll assume that this is a vector A and this is a vector B, and A cross B is A B sin theta. So A cross B is A B sin theta, and in terms of unit vector also you can write some unit vector has to be multiplied along the resultant vector. Okay, so that also we'll discuss. IDL and cross R vector. If I write this IDL cross R vector, then we know that if I hold a conductor like this, and suppose that the current is flowing from bottom towards top like this, then to find the direction of magnetic field, we have to hold the conductor like this, the curled fingers of your right hand and the thumb in the direction of the current. These curled fingers will give you the direction of magnetic field. So magnetic field will be like this, and at each point the tangent you draw gives you the direction of magnetic field. So that is the direction of magnetic induction. So in this case, if the current is flowing like this, I hold the conductor like this. So the current will be, the magnetic field will be, if the conductor is like this, and the current is flowing like this, magnetic field will be like this. From this side it is coming out, and this side it will go into. So this side the magnetic field will come out, and this side will go into the plane of the paper. So that should be, it should be like that only. Now, whether I will choose ideal cross R or R cross ideal, because A cross B and B cross A are not commutative. So I have to choose carefully the cross product of the two vectors. This is my ideal vector. This is my R vector, also in figure. This ideal is this vector, R vector is this vector. My B vector at this point, as I told you, if I hold this, the field will come out this side and enter this side. So the right side of this conductor, the field is into the plane. So therefore, it will be like that. Okay, these two lie in one plane, and this is perpendicular to the plane containing these two vectors. So I have to find a cross product of the two so that I get this vector. How to do that? If I find the cross product like this, from this to this, so the vector is out. So therefore, this is my ideal vector, this is my R vector, and here at this point, at the tip of this, the point lies where I want to find the magnetic induction, and that is point into the plane of the paper. It is like this. So if it is like that, I have to take the cross product. If I take the cross product like this, from this vector to this vector, R to ideal, this will be up. So this is not the case. If I take the cross product from this vector to this vector to this vector, then this is down. So this is correct. The correct expression is ideal cross R. That is in the direction of the required vector. So this is correct expression. But thing is that then we also know that A cross B is AB sin theta. So if I just open it up, this will be ideal R sin theta. But there is no R over here. Okay, there is no R over here. So I'll do one thing. I'll multiply one R here. So from that R, it will be ideal R sin theta, which is the opening of this, because ideal cross R is ideal R sin theta. Here only I have ideal sin theta, there is no R, so I'll multiply one R here and one R there. So this expression becomes this and divided by R cube. Okay, so this is the expression of vector form of Biot-Savart law. You can also write that ideal sin theta, this vector that I'm getting, I can multiply unit vector along this direction, because the magnitude is same. Whatever the magnitude is there, that is there. But if I multiply unit vector in that direction, then also I will get this. For example, the situation was mu0.45 ideal sin theta divided by r square. This was the scalar form. If I multiply unit vector to this in the direction of the magnetic field, then also I will get the expression. So this is a scalar, multiply the vector, it becomes a vector form. But what is that u cap vector? U cap vector is this, I call this vector dv. So you have to write the unit vector along this direction. Okay. So the unit vector along this direction is I'll write here this r cap vector. This is r cap vector, which is the given vector divided by its magnitude. Okay, this I can write like this. So if I multiply directly this value here, then this r comes here and this r goes there, and it will become r cube like this. So this is the vector form of Biot-Savart law. Now you can take integration on both sides to get the integral form of Biot-Savart law. that integral form is used when you have a large number of current elements. That means your conductor, you take each and every part of it and then sum it. The sum of all these which make up the conductor gives you the magnetic induction at that point. And by integration, you get the magnetic induction contributed by this conductor at this point. Now, we can also write the in current density form. In current density form also you can write. Current density is the current density J is a vector quantity. It is the current flowing through a conductor. Okay. Current flowing through conductor divided by its area cross section. Divided by area cross section. This is current density. So in this form also you can write. We have dV or B, whatever you say, equals to mu 0.4 pi ideal sine theta upon r square. Okay. If I take integrations, then this becomes B current density vector form. In vector form, already we have B equals to integration mu naught upon 4 pi ideal cross R divided by R cube. I don't want this, I want current density. So I'll introduce current density here into vector R divided by R cube dV, where dV is the volume of the element. This dV is called volume of the element. Because if I consider this as the length dl, area cross section is A, then volume of this small portion of this dl element is area into dl. So dl can be represented as the dv by area. So this dl is replaced by dv by A. So dv is here, A is area which can be represented as A, and A dl gives you the volume. If I write this as because I don't have the volume over there, so I'll the dl is replaced by dv by A, and J, for J I require I by A. So here this dl is dv by A and I by A is your J. So this is J, R and dv. Okay, if you rearrange it, it's like this. Again I am repeating, I dl R divided by R cube. I dl, what is dl? dv by A. So I'll write that here. This you can write as I dl is dv by A into R, cross product. Okay. What is I by A? I by A is J. So this will become J. This dv is volume taken out, cross R and dv. Okay. Or there it is R cube. So there it is R cube, R cube. So this is the form. This form and this form is the same. This is called density form. You have another form also, like you can express this Biot-Savart law in the form of charge and velocity, in the form of charge and velocity form. The B or dB is mu 0.4 pi ideal sine theta for r square. In vector form, we have 4 pi cross r divided by r cube. Now I want to introduce q and velocity in this expression. I is dq by dt. That means in place of I can write q or dq by dt time, and this r by t is the velocity. So then basically what it will be, I equals to q by t. So I'll write this as q or dq by dt, no problem, dq by dt. So this dl by dt into r vector divided by rq vector. This is your velocity. Okay, this is your velocity dl by dt, because what is flowing is current flowing through this length. Suppose it takes time dt to cross the length. The speed is this length divided by this time. So therefore, this is -0.4 pi q velocity plus qv r divided by r. Okay, thank you.